morning all, my name is Santhosh Kumar, Institute of Aeronautical Engineering. My subject is image processing. Today I am discussing about color image compression. So, color image compression. How we are compressing, what are the techniques and what are the types we will discuss. So, before going to the color image compression, what is that one means? Data compression. So, image is nothing but it is a set of data. So, data compression. A central role in the storage and the transmission of color images. The red, green and blue components of the pixels in RGB image, the means by the color information is conveyed. Compression is the process of reducing or elimination redundant and or irrelevant data. Suppose here we are talking about color image only. So color image in the form of red, green and blue. So this red, green, blue is in the form of data. Image in the form of data. So this data in the form of red, green and blue RGB, the pixels in the RGB of the image, the color information is conveyed. So what are the pixels are there? Suppose I am taking one image. That is a 3x3 size. So this 3x3 is a full of red, green and blue colors are there. So what are the intensities of there? Suppose I am taking red with 128 intensity, green with 98 intensity, blue with 120 intensity. So every image pixel, every cell, we have some different intensity values are there. So these intensity values in the form of red, green, blue only. So the red, green and blue of the pixels in the RGB, that means the color information is conveyed. So when we are going for the compression means definitely the image intensity values will be changed. So intensity values, how we are changing? The intensity values are in the form of red, green, blue only. So how we are changing? So definitely compression is nothing but we are changing the intensity values. So how we are changing? How we are eliminating the pixels in that one. So the compression is a process of reducing or elimination of redundant or irrelevant data. Unnecessary data we are removing or reducing the intensity or pixel size. Then only image compression is possible. But especially in the color image is form of nothing but it is in the form of red, green, blue only. So the data compression is a central role in the storage and the transmission of color images. So the data in the form of red, green and blue components of the pixels in RGB, that is a red, green, blue. That means the color information will be conveyed. So the color information will be conveying. So how I am conveying means the image in the form of red, the image in the form of green, the image in the form of blue. So that is intensity values. We are conveying the what is the data of the image. So the compression is the process of reducing or eliminating redundant and or irrelevant data. So what are the principal objectives? To minimize the number of bits required to represent an image. And image data compression methods fall into two common categories. What is that one? Information preserving compression and lossy image compression. So image preserving compression means especially for image RGB storage of legal or medical records. Compression and decompression is without losing of any information. So the lossy image compression is the provide higher level of data reduction, result in a less than perfect reproduction of the original image. So what are the principal objectives? To minimize the number of bits required to represent an image. Image data compression methods fall into two common: information preserving and lossy image compression. Suppose I am taking one image. This image I am taking as a 3x3 matrix. So if I am taking to minimize the number of bits, so number of bits in the image. So suppose I am taking 16 bit. So number of bits to reduce for image compression. For image compression, that is 8 bit. So originally 16 bit, but I have to 8 bit. Why? Because I need a compression. I need a compression. So for the compression, I need to reduce the image size or number of bits. So compression methods into two common categories: image preservation or lossy image preservation. So lossy image means, suppose unnecessary things are there. Suppose this pixel, these are empty, there is nothing is there. Here the pixel is a 10 is there, here nothing is there. Maybe the 10 means maybe it is a some disturbance or some blurring or any unnecessary some dotted lines are there from the original. So I have to remove this one. So this is I'm removing. So maybe the image lossy will be there. Why? Because it is a 4 by 5 4 matrix is converting to the 3 by 3. That means, is it lossy or not? Yes, 4 by 4 is converted to the 3 by 3. The image is lossy image. But what was happened? The unnecessary of the data is removing for the image compression. So it is one best example. Color image compression. It is the original image with RGB. That means red, green, and blue. So it is the figure B, the result of the compression and the decompression of the image. So here I compressed and decompressed. So what was happened means, unnecessary of the cells are removed. In the background, sir, if there any unnecessary are there, we have to remove. So how same here? What is the size? Suppose here 3 by 3 size is there. Here also 3 by 3 size is there. Is it reduced of the image size? No, it was not reduced. Why? Because all the image size, all the components of the background are same. But what was changed means intensity levels. Intensity values or levels. So the intensity levels or intensity values are changed from the original image. So the input image is a in the form of RGB, output image is a compressed or decompressed image. But what was changed is means only I changed the intensity values. So higher order has changed to lower order changed to higher order. So only the levels are changed, the intensity levels are changed, or unnecessary data is removed, or noisy data is removed. Then only the image compression is happen. But maybe sometimes the lossy of the data will be happen. But image compression is a need. So images are usually require an enormous amount of data to represent. Example, a standard 8.5 inches by 11 inches sheet of paper scanned at 100 samples per inch and quantized to 2 gray levels or binary image would require more than 100k bytes to represent 8.5 into 100 into 11 into 100 by 8. So that is the 1,16,875 bytes I need. So image compression involves reducing the amount of data required to represent a digital image. This is done by removing redundant information. Image compression is crucial for efficient storage of retrieval, transmission, and manipulation of the image. Suppose here they are taking one image. So this image I am taking as a 4 by 4. This requires enormous amount of data to represent a standard of 8.5 by 11 sheet of paper. So this image I am taking as a 8.5 into 11 inches of paper. The image is it in analog paper? Analog image. Paper means analog. So scanned at 100 samples per inch. So DPI, digital per input, is the 100. How many? 100 samples per second. So are quantized to 2 gray levels or binary image would require more than 100k bytes to represent. That is 8.5 into 100 into 11 into 100 by 8. So 11 inches is there. I need a 8.5. So 8.5 into 100 and 11 into 100 divided by 8. Total size is a 8 bit. So total size is 8 bit. 1,16,875 bytes data I need in this image. So it is not possible. Why? Because I need a image compression. So what we have to do? We have to do reducing the amount of data bits. So we have to reduce the bits. So these bytes, I am reducing the bits. So I am reducing the size. So this is done by removing the redundant information. Image compression is crucial for efficient storage, retrieval, transmission and manipulation of image. So if the image size is very large, what are the drawbacks? Suppose my image has a 1,16,875 bytes are there. It is more size. Okay, it is some problems will be occur. Why? Because the data size is more. So what are the problems we are getting facing with the more data is there means storage of the image, retrieval, transmission and manipulation of the images. These are the drawbacks with high data is there. So I want to reduce the data. So how we are reducing the bits means I am using image compression method. So more generally, data compression involves the efficient representation of data in digital format. Compression can be either lossless, information preserving or lossy. In lossy compression, one can achieve higher levels of data reduction with less than perfect reproduction of the original image. Data compression refers to the process of reducing the amount of data required to represent a given quantity of information. Various amounts of data may be used to represent or describe the same information. Some representations may be less efficient in the sense that they have data redundancy. Suppose I am taking image compression. Only possible with image in the form of digital image. So when the image is a digital image, then only compression is possible. Compression is possible. So digital image compressions are two types. Lossy compression. Second one is a lossless compression. So the data compression, the process of reducing the amount of data required to represent a given quantity of information. So when the compression can be lossless or information preserving or lossy. Lossy compression one can achieve higher levels of data reduction with less the perfect reproduction of the original image. So the various amounts of data may be used to represent or describe the same information. Some representations may be less efficient in the sense that they have data redundancy. So if N1 and N2 are the number of informations carrying units, example bits, in two datasets that represent the same information, the relative redundancy RD of the first dataset is defined as RD equal to 1 minus 1 by CR, where CR equal to N1 by N2. So it is also called the compression ratio. So it is also called compression ratio. So for the image, data redundancy can be of three types. So what are the three types means? First one is a coding redundancy. So we will discuss each one by one now. So if N1 and N2 are the number of information carrying units. Suppose I am taking N1 and N2 number of carrying units in two data sets that represent the same information, the relative redundancy RD of the first data set is defined as. Suppose I am taking data redundancy RD equal to 1 minus 1 by CR. So what is the CR here means? CR equal to N1 by N2. So N1 by N2 means what are the N1 N2? Number of units. So How many number of units means bits. Suppose N1 and N2 are the 16 bits are there. Example. So N1 by N2. CR equal to N1 by N2. So 16 by 8 I am taking. How much? 2. So CR equal to 2. 1 by RD equal to 1 minus 1 by 2. So RD equal to 0.5. So the compression ratio is a 0.5 ratio. The compression ratio is a 0.5. How we got means number of bits in a unit. So each unit has a number of bits. Here 2 units are there, N1 and N2, 2 units are there. So I am dividing with these things, then I will get the CR. The CR is a 1 minus 1 by CR, that is the RD, that is the redundancy ratio, redundancy value RD. Then I got the redundancy ratio RD equal to 0.5. But the images data redundancy can be of 3 types. So we are dividing as a 3 types of data redundancies. First one is a coding redundancy. This refers to the binary code words used to represent a gray levels. Okay. So binary code words used to represent a gray values. Binary to gray code words. So binary to gray, that is a coding redundancy. So a fidelity criterion or error criterion is required to quantify the loss of information, if any, due to a compression scheme. The objective fidelity criteria are based on some quantitative function of the original input image and the compressed and subsequent decompressed images. So suppose I am taking here root mean square, RMS error, RMS value I am taking. So RMS error means is there any data loss in the RMS value, which is the defined as the square root of MSE. Okay, square root of MSE. So a fidelity criteria of error criterion is required to quantity the loss information. Okay, in the we discussed here lossy and lossless. So lossy means error in data. Lossy means some data will be lost, that is an error. So a fidelity criteria or error criteria is a lossy information, that is due to a compression of the scheme. When we get the lossy, when we are having the lossy means when the compression scheme. So when we are going to the image compression, then only the data will be lost. The loss of information, that is nothing but a error. So the objective fidelity criteria are based on some quantitative functions of the original input image and the compressed and subsequent decompressed images. So I am taking root mean square of the error. So the data is error is there or not? Yes, the error is there when the data loss is there, when the image is a compressed image. So when I am going to the compressed image, maybe the data will be lost. That loss of the data I am taking as a RMS error. This RMS error is depend on square root of MSE, mean square root value. So E of m comma n equal to f dash of m comma n minus f of m comma n. Here f of m comma n is a original image, f dash of m comma is a reconstructed image, E of m comma is a error image. So error equal to, here I am taking compressed image subtracting with original image. Okay, suppose here compressed image is a some 1028 data is there, original image is a some 928 is there. So how much is there means 100 bits of data or images is compressed or error. Why? Because it is a lossy image. So E of m comma n equal to f dash of m comma n equal to f of m comma n. So the total error image equal to compressed image or reconstructed image subtracting with original image. That is the error value. So error E RMS equal to, why? Because I am taking means here you can see here RMS error. So E RMS or error E equal to 1 by Mn is equal into summation of n equal to 0 to m minus 1 or n equal to 0 to n minus 1 of f dash of m comma n minus f of m comma n whole square of 1 by 2. See here, I am taking one example of here 1 by 2. Here I am taking 1 by 2 value like this. So f dash of m comma n, f of m comma n is nothing but here e of m comma n, e of m comma n. So summation m equal to 0 to n minus 1, n equal to 0 to n minus 1 of e of m comma n whole square whole power 1 by 2. A related measure is the mean square signal to noise ratio. So signal to noise ratio. So the SNR, signal to noise ratio of RMS equal to summation m equal to 0 to m minus 1, n equal to 0 to n minus 1 of f dash of m comma n. So reconstructed image with total error value, error image. So the RMS value of signal to noise ratio denoted as SNR RMS is the square root of SNR RMS. When the ultimate image is to be viewed by a human, subjective fidelity criterion may be more appropriate. Here, image quality is measured by subjective evaluation by a human observer. Ratings by a number of human observers based on typical decompression images are averaged to obtain the subjective fidelity criteria. So, SNR, signal to noise ratio of the RMS value, is equal to the ultimate image is to be viewed by a human subjective fidelity criteria may be more appropriate. So the number of human observers based on typical decompressed image or averaged image by the subjective fidelity. Okay. So decompressed image or average data, both are the output images. So the examples of an absolute comparison scale, suppose I am taking the value equal to 1, what will happen? It is a excellent. Why I am calling excellent means an image of extremely high quality as a good as desired. If the value is 2, the rating is fine. An image of high quality providing enjoyable viewing, interference is not objectionable. When the value is 3, that is a passable. An image of acceptable quality interface is not an objectionable. And the fourth one is a marginal. An image of poor quality, we could improve it, interference is somewhat objectionable. Next one is a inferior, a very poor image, but you could watch it, objectionable, interference is definitely present. Unusable, an image so bad that you could be watch it. So the here SNR value, here the error, the images are in the error images are there. So how we are rating this one? I am taking the value 1, 2, 3, 4, 5 like this. So if the value equal to 1, excellent, there is no errors are there. So it is a extremely high quality of the image. If I am taking the value is 2, okay, why these are taking means here I am taking absolute comparison of the image compression. So if the value is 2, that is a fine, okay, not excellent, it is good. An image of high quality providing enjoyable viewing and interference is not objectionable. And value is 3 means passable. An image of acceptable quality, we wish to could improve it, and interference is somewhat objectionable. So here interference is not objectionable, but here somewhat objectionable means something happening, some error will be occurring. So inferior, a very poor image, but you could watch it, objectionable, interference is defined by the present. Okay, image is visible. Image is visible, but lossy. Okay, unusable. An image is so bad that you could not watch it. Okay, so it is a block diagram of image compression model. Suppose I am taking here f of m comma n, that is the input image. So input image means what will happen means source encoder, channel decoder, source decoder. That it is a f dash of m comma n. It is a output image or compressed image. So source encoder means we are converting to the f of m comma n. Is it any analog image, whatever it may be? Source encoder means we are converting into the binary form. Okay. Channel encoder means is there any noisy? Okay, it will be there. And channel encoder and channel decoder means we are removing the noise. Channel decoder means converting digital to analog. Here analog to digital. Here digital to analog. Source encoder means completely it is in the analog form, or f dash m comma n is a digital or analog form. Okay. So what are the components? What are the stages are there in the image compression? Is input with the source encoder, channel decoder, or source decoder. It is the f dash of m comma n. So the source encoder is used to remove redundancy is the input image. Channel encoder is to reduce the redundancy in a controlled fashion to help combat noise. Example of the parity bit. This provides a certain level of immunity from noise that is inherent in an or storage transmission system. If the channel is not prone to noise, this block may be eliminated. The channel could be a communication link or a storage or retrieval system. Channel decoder and source decoder invert the operation of the corresponding encoder blocks. So, source encoder is used to remove redundancy in the input image. So, the channel encoder is used to introduce redundancy in a controlled fashion to help combat noise, or example of the parity bit. So this provides a certain level of immunity from noise that is inherent if any storage transmission system. If the channel is not prone to noise, this block may be eliminated. The channel could be communication link or a storage retrieval system. Channel decoder and source decoder invert the operation of the corresponding encoder blocks. It is mainly concentrate our source encoder, decoder blocks, and not the channel encoder and decoder. So source encoder and decoder are the very important. So source encoder is the first stage. So source decoder is the last stage. So it is the A to D conversion. It is a D to A conversions. Okay. So what is source encoder and decoder? Source encoder is responsible for reducing or eliminating any coding, interpixel, or visual redundancy. So the first block mapper transforms the input data into a usually non-visual format designed to reduce the interpixel redundancy. This block is reversible and may or may not reduce the amount of data. Example, run length code encoding, image transformation. The quantizer reduces accuracy of the mapper output of according with some fidelity criteria. This block reduces psychovisual redundancy in usually not invertible. So already we discussed here. Source encoder is the first stage. Here it is the last stage. A to D and D to conversion. These are the major role in the image compression model. So source encoder is responsible for reducing or eliminating any coding, interpixel, or visual redundancy. So we have to remove coding or bit size. So the mapper is the input data into a usually non-visual format designed to reduce interpixel redundancy. So this block is reversible and may or may not reduce the amount of data. But what is the example means? Run length coding, image transform. So already we discussed in the previous topics, run length coding and image transformations are the best examples of source encoder and decoder. So the quantizer reduces the accuracy of the mapper output in the accordant with some fidelity criteria. This block reduces visual redundancy and is usually not invertible. So The symbol encoder creates a fixed or variable length code word to represent the quantizer output and maps the output in accordance with this code. This block is reversible and reduces coding redundancy. The decoder blocks are inverse operations of the corresponding encoder blocks except the quantizer block, which is not invertible. So the symbol encoder creates a fixed or variable length. Here I am taking source decoder, means digital to LR conversion, from channel to compressed image. So symbol decoder is to the this one and it is to the inverse mapper. So here channel decoder is coming from channel, source encoder, channel decoder, source decoder. So we can observe here it is the from the channel to the compressed image. Okay, after the channel means already the image is compressed. It is already compressed. So the compressed image with the symbol decoder and it is a inverse mapper. It is the output image with image compression. So symbol decoder and inverse mappers. So what is the symbol decoder, encoder and inverse mapper? So symbol encoder creates a fixed or variable length code word to represent the quantizer output of the maps of the output in accordance with this code. This block is reversible and reduces coding redundancy. The decoder blocks are inverse operations of the corresponding encoder blocks except the quantizer block, which is not invertible. So the basic comparison or basic compression methods of the image compressions are, so image compression with compression methods: Huffman coding, Golombe coding, arithmetic, LJW coding, run length coding, one dimensional, two dimensional, symbol based coding. Okay, so these are the 8 types are there. Majorly we are not using 8 types: Huffman coding, arithmetic coding, LJW coding, run length coding, symbol based coding. Majorly we are using Huffman, arithmetic, LJW coding, run length coding, and symbol based coding. Okay, majorly we are using 5 to 6 models. So the basic compression methods of some basic compressions are Huffman coding, global coding, arithmetic, LJW, run length coding, one dimension, two dimension, and symbol based. So what are the applications of the image compression? So image compression is a process applied to a graphics file to minimize its size in bits without degrading image quality below an acceptable threshold. By reducing the file size, more images can be stored in a given amount of disk or memory space. The objective of image compression is to reduce irrelevance or redundancy of the image data to be able to store or transmit the data into an bits required to represent the image. The image compression may be a lossy or lossless. Okay. So what are the applications? First application is a image compression process to graphical file. So we are converting to the minimize the size. So minimize size without reducing data loss. So the data loss will not be occurred. So the quality also good. So image quality is also good. So image compression is a process applied to a graphic file to minimize its size bytes without degrading image quality below an acceptable threshold. We are not changing any quality. We are not changing the image pixels or anything. Just we are compressing with the changing the intensity values. That is the image compression in a graphical file to minimizing the size of the bytes. By reducing the file size, more images can be stored in a given amount of disk or memory space. So the objective of image compression is to reduce irrelevance or redundancy of the image data to be able to store or transmit data in an efficient form. It is concerned with minimizing the number of bits required to represent an image compression or lossy or lossless. Already we know that the images are two types, lossy or lossless. So data compression is nothing but a image in the form of image is nothing but a data in digital form. So the data role is a storage of transmission of a color image. So it is nothing but a image is nothing but a data. So the data in the form of RGB, red, green, and blue. Why? Because it is the color image compression, not the gray. So it is a process of reducing or eliminating redundant or irrelevant data or unnecessary data. So what are the principal objective means? To minimize the number of bits or image compression into two common methods: information preserving, loss image compression. So here input image and output image, but input image is a RGB, output is a image is a compressed or decompressed image. So images are required an enormous amount of data. So any of the data is in the form of analog or digital form. We have to convert it into the digital. Then only we are reducing the image size or bits, number of bits or number of samples of the image we are reducing. Then only it is possible to reduce the image. So it is done by removing the redundant information. The image compression is crucial for efficient storage, retrieval and transmission, or manipulation of the images. So generally the data compression involves the efficient representation of data in digital format. So compressions are either in a lossy or lossless. So data compression refers to the process of reducing the amount of data required to represent a given quantity of information. So the various amounts of data may be used to represent or describe the same information. Some representations may be less efficient in the sense the data in the redundancy. Suppose I am taking two number of units N1 and N2. Why? Because any image we have to take N1 and N2 are the units. Okay. So these are the two units in the bits, the form of bits, the two data sets that represents the same information, and the relative redundancy are the data in the first data set is defined as RD, redundancy data redundancy RD. Data redundancy RD. So RD equal to 1 minus of 1 by CR, where CR equal to N1 by N2. It is also called compression ratio. So the images or data redundancy can be of three types. Coding redundancy. This refers to the binary code words used to represent in a gray. So a binary is converting to the gray. So if fidelity criteria or error criteria is required to quantify a loss information or due to a compression scheme. Objective fidelity criteria are based on some quantitative function of the original input image and the compressed image. So root mean square or MSC, square root of MSC are the color image compression errors. So the error E of m comma n equal to f dash of m comma n minus f of m comma n. Here f of m comma n is a original image, f dash of m comma n is a reconstructed image, E is the error image. So error image E equal to 1 by mn. It is a summation m equal to m minus 1, n equal to n minus 1, f dash of m comma n minus f of m comma n whole square by 1 by 2. It is a error in RMS value. So the RMS value of the signal to noise ratio is denoted as SNR RMS in the square root of SNR RMS. When the ultimate image is to be viewed by a human subject to fidelity criteria may be more appropriate. So the decompressed image or averaged images are in the form of image compressions. So these are the absolute comparison values of the image compression levels. If the value equal to 1, that is excellent, means the image is good quality. If the value is 2, means the image is somewhat fine, that is high quality but enjoyable viewing, but interference is not objectionable. Okay, errors are maybe occur, but not a mandatory thing. It is a very less images noises are there, and passable when the value is 3. If the image is acceptable but interference is objectionable, some errors may be there, but it will be not be highlighting in the image. And value is 4, that is a marginal, that is the image is a poor quality but interference is somewhat objectionable. Okay, it is a visible of the image, but it is not a objectionable. But inferior is a level 5 when it is a poor quality of the image, and it is a definitely it is a interference is there. And unusable means not in use. Why? Because image is not visible, not visible, and data loss. That is the errors are there, are objectionable. Why? Because it is a interference is there. Okay, it is a block diagram of image compression model. Input is equal to f of m comma n is a input image. uh, First stage is a source encoder, analog to digital compression. Channel encoder is a noise will be happen, it is be removing. And this channel is a channel means where we are finalizing, means we are compressed image. Okay, compressed. Okay, channel decoder means digital to analog conversion. Source decoder means final output of the image without data loss or data loss may be there. That is a compressed image, that is a f dash of m comma n. So source encoder is used to remove redundancy in the input image. Channel encoder is used to introduce redundancy in a controlled fashion of the help parity bit. This provides a certain level of immunity from noise into the inherent. So the channel could be a communication link or a storage retrieval system. Channel decoder and source decoder are the operations of the corresponding encoder blocks, and mainly the source encoder and the decoder are the important, are the final stages, are the channel encoder and decoder steps. So what are the source encoder and decoder means? Source encoder is the responsible for reducing or eliminating the coding of the image. So source encoder and decoder, okay, first stage and last stage are very important role, because first stage A to D, first stage D to A. So in the mapper, run length coding, image transformations are the major role in source encoder and decoder. So the quantizer reduces the accuracy of the mapper output in accordance with some fidelity criteria. This block reduces a visual redundancy or usually not invertible. So the symbol encoder creates a fixed or variable length code word to represent the quantizer output and maps the output in accordance with this code. This block is reversible and reduces coding redundancy. So the decoder blocks are inverse operations of the corresponding encoder block, except the converter block, which is not invertible. Okay. So here decoder means I am taking as a here quantization. Quantization of the image with samples. So from channel, compressed image, symbol decoder, inverse mapper. These are the final stages before the compressed image. So what are the methods or the image compression models? Huffman coding, global coding, arithmetic, LJW coding, run length coding, one dimensional compression, two dimensional compression, symbol based compression. So these are the final compression models, and applications are image compression is processed to a graphical file to minimizing the size or bytes without degrading image quality and reducing the file size. More images can be stored in a given amount of disk or memory space. In the less space, more data to keep. So less space, more data to be keep. How it is possible means image compression. So the objective of the image compression is to reduce irrelevance and redundancy of the image data to be able to store or transmit data of an efficient form. It is concerned with the minimization of number of bits required to represent of an image. That is the image compression may be a lossy or lossless. These are the references for the image compression topic or digital image processing. Okay, thank you.
Like, share, and subscribe. Hit the bell icon for more updates.